Hi everyone, today we're going to be talking about topic 7.11, Introduction to Solubility Equilibria. So when thinking about solubility equilibria, we need to think first about ionic compounds. There's a few things to remember about ionic compounds that are important, and one is that they dissolve completely in water. And anytime you write an equilibrium, where something is dissolving, something being an ionic compound, the solid equals the reactants, and the ions are the products. So if I have the equilibria of some sort of a solid AB, right, this is an ionic compound, that's an equilibrium with A plus aqueous and B minus aqueous. This will have an equilibrium constant K, and the K for dissolutions is called the solubility product. And we give it the subscript KSP. And so if you see this, you essentially think ionic compound is dissolving in water. So if you're dissolving something, it has a very special equilibrium constant, and that is a solubility product. Let's look at two examples of what this looks like, because all solubility product equilibria look pretty similar. Let's say I have barium sulfate. This is a solid. I then dissolve it in water, and it has this equilibrium. Ba2 plus aqueous plus SO4 2 minus aqueous. If I'm going to write my expression for K here, KSP is going to be equal to its products over reactants. But remember, solids don't count. So here, KSP is just the concentration of Ba2 plus ions times the concentration of SO4 2 minus ions. And pretty much every KSP looks like this. You normally don't have something in your denominator because your denominator is normally a solid. Remember, solids and liquids do not show up in the expression for K. Doesn't matter if it's a KSP, a KC, KP, or in the future we'll get into KA and KB. It doesn't matter. Solids and liquids never show up in those expressions. Another example here is, let's say we now have barium phosphate, Ba3 PO4 2. Right, this is a solid. You dissolve it, we end up getting 3 barium 2 plus ions and 2 phosphate ions. Right, all of this is balanced. If we do a expression for K here, KSP is equal to the concentration of Ba2 plus cubed times the concentration of PO4 3 minus squared. And so the same rules apply for KC and KP as they do for KSP. It's just the event is different. Now, there's a few key terms to keep in mind here. For one, the biggest key term that I'll underline here is that KSP is not the same as what we call solubility. Solubility is the quantity or amount of substance that dissolves to form a saturated solution. Saturated solution basically means ions completely dissolved to the point where no more ions will go in solution. The idea here is, say I have a solution of salt water, I can keep putting salt in it, but eventually you won't have enough water to have IMFs with the salt, so no more is going to dissolve. That is essentially when you've reached saturation, right? When no more ions will dissolve. Solubility, and we'll get into this in an example in a bit, is X in our ice table or our rice table. So when you're solving for X, that's what solubility is. You'll see it in grams per liter, or you'll see it in molarity, which is moles per liter. So KSP is the maximum amount of ions that can be present in solution before a precipitate appears. Essentially, this is the point at which saturation, where you can't have any more ions in solution, occurs. So solubility product and solubility are different terms. Solubility is the amount that dissolves to form a saturated solution. KSP is the maximum amount of ions that are present before you start precipitating. And here's just kind of a helpful flow chart to kind of help you out with things. If you're given the mass solubility of a compound, right, how soluble it is in grams per liter, using the formula weight, you can convert down. Using the formula weight, you can convert this to molar solubility in moles per liter. Then using the empirical formula, you can get the molar concentration of ions. And so if you have, for example, the concentration of Ba2+, right, that's the molar concentration of ions. And then using that with your expression for KSP, you can calculate your KSP. And you can go in the opposite direction. So from KSP, I can get the concentration of ions. Using the empirical formula, I can find the solubility of the compound in terms of the moles. And then using that and the formula weight, I can find the mass solubility of the compounds. And this is something we're going to have a little bit of practice with in the next few examples. So in this problem here, we're told the KSP for calcium fluoride is 3.9 times 10 to the negative 11th at 25 degrees Celsius. We're asked what's the molar solubility. Remember, if you're ever asked for the molar solubility, you're essentially being asked what is X in the rice table. So here, first thing you need to do, of course, with rice, is write the reaction. So any dissolution process, you start off with the solid, which is CaF2. This is an equilibrium with its two ions. We have Ca2 plus aqueous plus 2 F minus, not Fe, F minus aqueous. It's very important that we're comfortable with being able to translate these formulas into their constituent ions, and also remember our polyatomic ions, since that will be tested heavily in this particular section. The next part is to look at the initial concentration. Fully fill out this table. And at this point, you might be wondering, well, what do I do for the initial concentration of calcium fluoride? So now if we think about this in relation to our equilibrium expression, right, calcium fluoride can't show up because it's a solid. And so you actually don't have anything for this initial concentration here. We don't have to worry about it. For calcium 2+, that's 0 because the reaction hasn't started, or at least the dissolution hasn't started. And for F-, that's also 0 because it hasn't started dissolving. For change, well, because we didn't really start anything with CaF2, again, we don't have to write anything there, and we're not interested in that. For calcium, it's plus X because we only have 1 in our coefficient here. And for F-, we have 2, so it's plus 2X. And then for equilibrium here, again, CaF2, we don't really need to worry about that part of the expression. For calcium 2+, it's plus X, and for F-, it's plus 2X. And then all we need to do now is just plug into our expression for KSP and solve for X. So, KSP is equal to the concentration of Ca2+ times the concentration of F- squared. That's going to be equal to 3.9 times 10 to the negative 11th. So all we're doing at this point is solving for X. So KSP is equal to X times 2X squared. That's going to be equal. All of this is equal to 3.9 times 10 to the minus 11. And so now all we got to do is just multiply these together. 4x cubed, right, because you square the 2 and then multiply the x together. 4x cubed equals 3.9 times 10 to the minus 11. And at this point, you just solve for x. In this case, x will equal 2.1 times 10 to the negative 4th molar. Right, think about the concentration here, or think about our units here. KSP, that is in that is a unitless number, but we're solving for concentration at the end of the day. So you should have your unit here be molar. And so the solubility of calcium fluoride, CaF2, is 2.1 times 10 to the negative 4th molar. I mentioned before there's two different units that we can use here. One is moles per liter, which is of course what we have here in molar, but we also have grams per liter, and this is the solubility in terms of grams. And all you need to do here is just multiply it by the molar mass. And so here, molar mass of calcium fluoride is 78.07 grams per mole. Your moles cancel out, and then our answer now for x is going to be 0.016 grams per liter. So what this is saying, and I'll write this out in plain English, is you can dissolve 0.016 grams of CaF2 in 1 liter of water. If you try to put more, let's say I put 0.02 grams per liter, 0.02 grams of calcium fluoride in 1 liter of water, the 0.016 will dissolve, and you'll have 0.004 grams of calcium fluoride that does not dissolve. That's what this is essentially trying to tell you. Here's another example. I encourage you to try doing this one on your own to see if you can solve for x. First, solve it in moles per liter, and then try to convert it to grams per liter. I'm going to solve it right here so you can kind of see what's going on, but I encourage you to try and solve it on your own first. All right, this is pretty similar to the previous example, although it might be a little bit easier. So again, we're using a rice table. We want the molar solubility, and so that's in moles per liter. Of course, you can take that a little bit further and do it in grams per liter. But for solubility, we're essentially solving for x. So R, we have barium sulfate, BaSO4, solid. This is in equilibrium with Ba2+, and SO4, 2-. Again, we must remember our polyatomic ions, or else this unit and continuing on will be very, very difficult. Initially, BaSO4 is not in solution, so we don't really have to worry about BaSO4. It doesn't show up in our expression for K. Barium and sulfate are both 0 because they don't show up at the start of the reaction. They only show up after you've dissolved it. For change, again, we don't need to worry about barium sulfate. For Ba2+, it's X, and for SO4 2-, again, it's plus X because the coefficients are only 1. And then finally, at equilibrium, again, we don't need to worry about barium sulfate. For Ba2+, it's X, and for SO4 2-, it's also X. So if we do our expression for KSP, this is equal to 1.5 times 10 to the negative 9th, and that is equal to the concentration of Ba2+ times the concentration of SO4 2-, which is just X times X, or X squared. So all you do is take the square root of 1.5 times 10 to the negative 9th. And so X is equal to 3.9 times 10 to the negative 5th. And this will be in moles per liter. Now in grams per liter, this is going to be 3.9 times 10 to the negative 5th moles per liter times the molar mass of barium sulfate, which per mole is about 233 grams per mole. I'm not going to write the entire thing, but this is going to be equal to 0.0091 grams per liter. So I can dissolve 0.0091 grams of barium sulfate in water per 1 liter of water before it starts to precipitate. Now, thinking back to Le Chatelier's principle, and I've been asked this question before, and I said that eventually we would learn why things precipitate. Here is the mathematical and physical reason why. A precipitate will form when Q is greater than KSP. In other words, the reaction shifts towards the reactants, which is a solid precipitate. In that previous example, if I have BaSO4 in equilibrium with Ba2 plus and SO4 2 minus, if Q, right, which our expression for Q, is just going to be equal to concentration of Ba2 plus times concentration of SO4 2 minus, if this is larger than K, it means that the concentrations here are really high. If the concentrations there are high, based on Le Chatelier's principle, it wants to go left. And so when Q is larger than KSP, you get precipitation. And that's how we can determine if a reaction will precipitate or not. So let's just look at one more sample problem here together. This is an AP Classroom problem. You have barium iodate, and that is in equilibrium with barium 2 plus and iodate ions. It has a KSP of 4 times 10 to the negative 9th. So it's asking, according to this information about the dissolution of barium iodate, what is the correct value of S? S is just another word for X, is another letter for X. Of course, that's the solubility of barium iodate. So it says you can calculate it using which of the following mathematical relationships. So you don't actually have to calculate the number, but it's essentially getting you to think about the Rice table. So again, R here, it's given above. Initially, doesn't matter what I have for barium iodate because it's not in equilibrium since it's a solid. I have no barium and I have no iodate because it's the start of the reaction. Again, barium iodate doesn't matter. You can just cross all those off in your Rice table. This will be plus X. This will be plus 2X. And then, of course, at equilibrium, you have X molar barium and 2X molar iodate. And then we just plug that in to KSP. KSP is equal to 4 times 10 to the negative 9th, which equals X times 2X squared, which equals 4X cubed. Now, if we look, of course, in this problem, X is just S, so this is 4S cubed equals 4 times 10 to the negative 9th. And if we look, that is expression D right there. We'll talk about this a little bit more in the next class, but for now, that's all. Thanks, guys.